Hello everyone, I'm Tishaki from the Mathematics Department of Xiamen University, Malaysia, and this is my project presentation from MAT202, Mathematical Analysis 2. Today, I'll be presenting a fundamental result in multivariable calculus that help us understand how nonlinear functions behave near a specific point. It is called first-order approximation theorem. Let's begin by understanding the motivation. In multivariable calculus, nonlinear functions can behave quite unpredictably near different points. The first-order approximation theorem helps us locally approximate such a function using a linear one. This means we can treat a complicated function as if it were linear, but only near a specific point. Simply to say, this theorem tells us that near a given point, a nonlinear function can be closely approximated by a linear one. To help visualize this idea, take a look at this simple example. The surface z equals to x squared plus y squared. This surface is curved, but at the origin, we can draw its tangent plane, which serves as a flat approximation to the surface near that point. You can see in the figure that the tangent plane touches the surface exactly at the point origin, and at that point, both the surface and the plane share the same height and slope. If we zoom in very closely near that point, you will notice something interesting. The curved surface and the tangent plane almost overlap. They become visually indistinguishable. This is because the error between the two becomes infinitesimally small as we approach the origin. While this is just a 3D example to help us build intuition, the same principle applies in higher dimensions, even when we are approximating vector value functions. This is a core idea behind the first-order approximation theorem. A differentiable function can be approximated locally by a linear map, and the approximation improves as we get closer to the best point. This type of approximation is very useful. It appears in optimization, numerical methods like Newton's method, and even in machine learning, where linearization plays an important role. This is because linear functions are much easier to analyze and compute. Today, we will go through the definition, state, and prove the theorem, and finally, go through an example to see it in action. Let's begin with the formal definition of order of approximation. Given a function f from Rn to Rm and a polynomial mapping G of degree at most 1, meaning it is linear plus a constant vector, we say that these two functions are kth order approximation of each other at x0. If the pointwise difference between the function f and g goes to 0 faster than norm hash power k. In our case, since we are dealing with first order approximation, our k is equals to 1. Here we clarify what a polynomial mapping of degree at most 1 looks like. It can be written as gx equals to ax plus b, where A is an m times n matrix and b is a constant vector in Rm. Note that the mapping G is a linear transformation if and only if b is equals to 0. This is essentially a linear transformation with a translation. Think of it as a tilted plane in space. Now, let's state the main theorem. The first order approximation theorem says, if a continuous function f has a polynomial map G of degree at most 1 that approximates f to first order at x0, then f is differentiable at x0. Conversely, if f is differentiable at x0, then such a polynomial map exists and is unique, and it is given by the Jacobian matrix times x minus x0 plus the value of f at x0. This theorem provides a bridge between the concept of differentiability and the idea of approximation by linear functions. So, what is the intuition behind this theorem? Well, differentiability at a point means that the function behaves almost like a linear transformation near that point. So it makes sense that there would be a linear map, a degree 1 polynomial that gives a very good local approximation. If such a linear map exists and works well enough, then the function must be differentiable. Conversely, if a function is differentiable, we can construct this map directly using its derivative. Now, we begin the actual proof. Let's first prove A. If f has a polynomial approximation g, then f is differentiable. Let's assume that g is a degree 1 polynomial map, written as gx equals to as plus b, and it is a first order approximation of f at x0. By assumption, the limit of the error goes to 0. This implies that the function f and the linear map ax plus b agree very closely near x0. Their difference is negligible compared to the size of hash. Then, by taking the limit inside, we see ax0 plus b equals to fx0. So, we rearrange the expressions and get a new form. The limit of the difference between fx0 plus hash and fx0 plus a hash also tends to 0 over norm hash. This matches the definition of differentiability. Therefore, we have proven that if a first order approximation exists, the function is differentiable. Now we prove B. If f is differentiable, then such a polynomial approximation g exists. From the definition of differentiability, the linear part t hash must exist such that the error term vanishes. This t hash can be written as matrix A times hash. Then we found that each partial derivative is a column of the matrix A. So A equals to df x0, which is the Jacobian matrix. So we get this limit equals to 0. Then we construct the function gx equals to fx0 plus the Jacobian matrix, and then times with x minus x0, which is a degree at most 1 polynomial. Hence, we have this limit which confirms that g is a first order approximation of f at x0. Let's look at an example to visualize what we have just proved. We return to our function fxy equals to x squared plus y squared. At the base point 1, 1, the tangent plane approximates the surface. The gray line connects the true value of fx0 plus hash and the approximation. The red dot shows the actual function value, and the green dot is from the linear approximation. As you can see, the closer hash is to 0, the smaller the error. Now, let's look at a concrete example. We define a function f R4 to R3, and we want to find its linear approximation near the point x0 equals to 1, 2, 0, and -1. We first compute the Jacobian matrix. That is the matrix of partial derivatives. Then, we evaluate the function f at x0. Then, we compute ax0 and subtract it from fx0 to get the constant vector b. So finally, the linear approximation is gx equals to ax plus b, where A is the Jacobian matrix and b is 0, 0, 1. This example shows us exactly how to apply the theorem and verify that the approximation holds. To conclude, the first order approximation theorem allows us to treat nonlinear functions as linear in small neighborhoods. Also, the Jacobian matrix plays the role of the best linear predictor. This theorem not only categorizes differentiability but also gives a concrete way to construct the linear approximation. Here is the reference used for this presentation, and that's all from my presentation. I hope this video presentation gave you a clearer understanding of the first order approximation theorem. Thanks for listening.